Welcome to qnawire.
So for this question, we're going to start off with this expression for the total potential energy to find what is the force that is exerted on an ion. Now the force we know is related to potential energy by negative du over dr, which in this case, if you were to differentiate this, you will get negative alpha ke square over r square plus b times m over r to the power of m plus 1. So this after differentiating. Now at the equilibrium point, that is when r equals to r naught, the equilibrium point, we expect that the net force acting on the ion must be 0, right? So that it doesn't move, right? So it's in equilibrium. So if you want to find what is our unknown b, we can actually get set f equals to 0 when r equals to r naught, and try to rearrange the equation a bit. Right, so this is the expression, and if we were to rearrange this to find what is b, we should get b to be alpha ke square over m times r naught m minus 1. Now substituting this value of b into our expression for f, alright, so now we have two different r's. We have one r naught, which is a constant, the equilibrium spacing, and we have r, which is the variable. So now we can simplify the expression for the force a bit from here by opening up the brackets and looking at the common terms, which is alpha ke square over r square should get 1 minus r naught over r to the power of m minus 1, which is the expression that is given in the question. Right, what you have to do over here is you just have to pull out r square from this. This is just r square times r to the power of m minus 1, right? And then we can combine these two together, r naught over r to the power m minus 1. Now for the next part of this question, we want to imagine that the solid is now displaced by a small distance s. So basically we are looking at our r becoming r naught plus some small distance s, right, from the equilibrium point, and we want to find what is the force that is acting on it. Alright, so this is the expression. Now since our our R is now given as R naught plus S, we can actually replace R naught as R minus S. So this will become, just focus on this bracket over here, or rather let me just focus on the inner bracket. This to be just R minus S over R to the power of n minus 1, which is 1 minus S over R. And because S is very small, much smaller than R, so we can use the binomial expansion for this. So undergoing binomial expansion, we take the term which is negative S over R multiplied by the power n minus 1 plus so on and so forth. Right, but we ignore the higher powered terms, we just truncate at the second term. So this is just an approximation because our S is much less than R, so this term is very small, right, less than 1. So we can use the binomial expansion. Putting that in back into the expression for force, expression for the force becomes negative alpha ke square over R square, 1 minus 1 plus S over R n minus 1. This becomes alpha, negative alpha ke square over R square times S over R times n minus 1. Rearranging this a bit, get negative alpha minus 1 times S. So now remember that our S is very small, so R is actually can be approximated as R naught, because S is very small. So this is approximately just negative alpha ke square over R naught cube times n minus 1 times S. And we see that this is kind of like the Hooke's law, where this is our spring constant K and S is the small displacement. And this K is indeed what is given in the question. Right, we want the K to be this Ke alpha E square divided by R naught square, R naught cubed times n minus 1. So now we're going to put some numerical values into this expression to find the frequency of vibration. So frequency of vibration, we can assume because it is a small displacement, it acts like a simple harmonic motion. So the frequency is just equals to 1 over 2 pi times square root of K over M. So the K value, as described earlier, is alpha Ke square over R naught cubed n minus 1. We will have to find what is R naught. So from the figure 38.22, we actually see that the interatomic distance between sodium ions in the sodium chloride crystal is 0.562737 nanometers. This between sodium and sodium. But what we calculated, the R naught over here, is the distance between sodium and chlorine. So approximately we have one chlorine with one sodium, so approximately halfway in between would be the chlorine nuclide, right? So we expect the distance for R naught to be about half that of this distance between the sodium ions. So this is approximately 0.2814 times 10 power minus 9 meters. So using this, we can actually calculate our K, right, the stiffness constant, putting in alpha to be 1.7476. K is just 8.99 times 10 power 9. E is elementary charge squared. We have the R naught 2.81 times 10 power of minus 9 cubed. Sorry, this is 2.8 times 10 power minus 10. Right, so we have shifted the decimal point by 1, so this is minus 10 cubed, and then we have m minus 1, where m is 8, so 8 minus 1. And we should get a constant about 127 newtons per meter. And now we are ready to find the frequency. Over 2 pi. Then we have 127 at the top, and we have the mass below. Right, so for the mass of the sodium ion is 23 atomic mass units. So we gotta convert this into kilograms. Now evaluating this, we should get 9.18 times 10 to the power of 12 Hertz.